We're going to talk specifically about coil on plug and coil near plug scope analysis. We're going to analyze these with voltage and current on the lab scope. There are two common circuit arrangements that will be covered in detail. We're going to use the wiring diagrams or circuit diagrams to show you what to test and how to determine what you're looking at. Then we're going to show you photos that will show you where to connect your test leads. And at the end, we're going to tell you how to integrate this as part of your overall diagnostic routine. We're looking at a crankshaft input signal here, goes to the PCM. Now we must use crank and cam because the PCM, or whatever the control unit is going to have total control over firing each individual spark plug. Just like we had sequential fuel injection where the computer fired each injector at the proper time. We've gone one step beyond that now. We're going to fire each coil or coil unit. And we'll talk about those later. But let's talk about these crank and cam for a moment. There are two basic types of pickups we're going to use on cranks and cams. The two wires are usually magnetic pickups, meaning they have a magnetic pickup that goes in adjacent to a rotating gear or something that has gaps in it and causes changes in the magnetic force. There are three-wire pickups, and they function mainly by Hall effect principles. Either magnetostrictive, which is where they have a magnet built into the pickup itself and they're operating near a gear or a toothed device, or a field interruption where there's an actual vein interrupting them. And there are combination pickups that house more than one sensor. Don't be confused by that. They're going to work by one of these two principles. It's going to be the same thing. If you want to know more about diagnosing in depth with crank and cam pickups, go look at that section, because there's some advanced diagnostics we're going to cover, and we don't want to cover it in every section. This is specifically talking about the COP system. And we get to the COP, or the coil near plug, whichever one you're going to use, we're going to talk about the two main circuit arrangements. Two-wire COP units, or circuits, are where there are B+ connected to one side of the coil, and the PCM, or control unit, supplies ground to the other to energize the coil and build up a magnetic field. There are four-wire COP units that have a digital signal sent from the PCM that controls current flow. Quite often these are referred to as having an amplifier inside. Whichever terminology we're going to use, the coil unit itself is going to look at the signal and turn off current flow and turn on current flow. So it's going to be doing it while under the command of the PCM, but the COP unit itself must perform that function. Now we're going to show you how to determine the circuit type from a wiring diagram so you won't have to figure it out. Let's look at this wiring diagram. We see right here we have B+ on this red wire going to all the coils. Now we've already talked about these cam and cranks. Let's bring up the middle so we can look at just the COP units. We've talked about the left side. You notice it has ECM power relay. It's coming over and going through splices and going to all the coils. We're going to say this one time. When we say check B+, if this voltage is not right, the coil is not going to have full output. You may have something no more complicated than a charging system problem, reducing voltage to the coil. Pay attention to things like battery voltage. We have to say that because we get into this advanced diagnostics. Sometimes we forget the simple things. Now, on the other side, we have a PCM or control unit. This happens to be a Ford PCM. It's going to turn on ground to build a magnetic field about each coil and turn it off. In this case, the PCM is the ignition module, and this is a simple coil. One way of making it work. Here is the signal we're going to be getting. Now, we have a whole section on primary voltage waveforms along with primary and secondary for advanced diagnostics. And to make this easy to find, we try to separate these out so we don't teach the same thing every time. Here we're focusing on diagnosing coil on plug and coil near plug. And so we're going to get this signal. And this signal is caused because the PCM is acting like an ignition module. So when we connect into the PCM, we see this signal. It is a primary voltage waveform. Let's look at a few things about those primary voltage waveforms. As we said earlier, we're going to have an entire section on primary and secondary. We'll show you more about that. They're going to apply to all types of ignition. The reason we've separated them out is because primary and secondary goes from everything from distributors to DIS to coil on plug to coil near plug. And the diagnostic is universal. We can look at the voltages and patterns and diagnose some advanced things. You're going to see how we're going to use them to diagnose things like fuel lean out, weak coil output, EGR problems with these waveforms. But remember, we're also looking for the proper voltages and things applied to the coil. Now this example is a coil near plug because it's a GM. It has a small plug wire that uses 4 wires. Now remember, there are only 2 basic families. They have 2 or 4 wires. Like we did before, let's take this big diagram and zoom in on the center part. Now, right off the bat, we see that there's a ground over here. Look, we're looking at ground 112 on the left side of the engine. And as we notice, this ground goes over and supplied to each one of the coils on pin A. Let's not call these coils, let's call these COP units, because they're really a module. There's an amplifier built inside, and we'll see how it's going to work. So we've seen ground, no longer supplied by the PCM. At the bottom, we see a fuse, ejector fuse number 1. Ejector fuse 1, fuse number 22. It's a 15 amp fuse. And it supplies voltage up to pin D on all of these modules. Now remember, we cut this in half, so we're only looking at half the engine. We're looking at 1, 3, 5, 7. What's going on the other side of this module? Well, the other side, all of them connect to a common reference low, which is GM's way of using their system to supply a reference for a digital signal to the module. It's not ignition ground. It's raised slightly above ground with a pull-down resistor so that the module grounds itself through the black wire over at ground 112. GM doesn't want to ground it in through the center. What else is going on over here? Well, look, we have each individual module is controlled by a digital signal. It's going to be 5 volts going to ground. That's what the switch inside means. When the circuit is open, switch is open, we supply 5 volts. When we close it, it goes to ground, which signals the module on pin C to start current flow into. We'll see how that works. Regardless of the circuit configuration, each COP must receive B+. We can't say it enough times. We found problems that were impossible to find by going back and finding simple problems with B+. And they're not always simple. I'm oversimplifying it. We'll talk more about that later. But if B+ and ground are normal, the current flow in the circuit is determined by the COP unit. Let me say that again because this is too simple. If we got a good ground and we got a good B+, the COP unit determines current flow. Now, what we're saying this for is to remind you that you must check B+ and ground. We can't say it enough times. We're going to use low current scope patterns to help identify circuit and COP problems along with voltage scales. Now, let's see how this works. We're looking at current flow here through the COP unit. This red trace. Now, the red trace goes up. Notice that there is a scale on the right. This is reading our amperage right at 15 amps. We've set our scope up on a 20 amp scale. This is measuring current flow. So what the low current probe does is change this into a signal that can be displayed on a scope, and it gives us a reading. Now this scope, our Pico, is set up to automatically scale in amps. Some scopes you must read millivolts because they read the voltage. We have specific training. We have two other patterns on here. Let's go talk about these other patterns. But primary amps are in red. This is current flow produced in the COPS unit. Now this is a 4-wire COPS unit. So this current flow is a function of the power and the ground on the left we saw. And then the COPS unit itself turns on under control of a signal. Here's how we connect our leads. We said we're going to show you. Look at the top right corner. You will see a coil on plug. You got a Hall effect pickup going around the red wire, and we got a voltage clip going here. If we put this amps probe on wrong, and it's going the wrong direction, you saw that plus sign, it will go off scale when current increases. No big deal. Disconnect it, re-zero it, turn it over the other direction. It is directional. It looks at which direction current flow is going. So if you make a wrong connection, it's going to go off the screen to the bottom. Turn it over, you'll get a normal pattern. Let's look at this blue trace here. This blue trace is spark control. We call it spark control because there's no real name. Some people call it ignition control. Everybody has their own magic name for it because no manufacturer wants to be saddled with someone else's name. Well, what is this? This is controlling current flow, which in turn is going to control spark. Look, when it goes up, current flow starts flowing. When it goes down, current stops. This is the PCM controlling spark. How does it do it? With a digital signal. Looking over to the right, we find that this signal is just slightly less than 5 volts. Look, it's not quite halfway up between the 4 and the 6. Exactly halfway would be 5 volts. To get real picky, it's around 4.7 volts in this GM. And if the amplifier gets bad, this voltage will be too low. Let me say that again because that rolled off the tongue too easy. If we have problems, one of the ways this module goes bad, this COPS unit, Coil On Plug in this case, if it goes bad, this control signal is lower than normal because the amplifier is not amplifying properly and it pulls this circuit down because it's a pull-up circuit. Doesn't matter if it works on 12, 5, whatever the voltage is. If there's a problem in the module, one of the problems can be it pulls it down. We've got other things that can go wrong with the coil. We're checking other ways to find that. We have a third signal here. Look at the bottom. We've got ignition secondary in kilovolts, thousands of volts. It's rocking along and suddenly drops down when we turn current flow on. That's the magnetic field building up. And that takes a period of time. It happens at the same time current flow starts. Let me give you a hint here. Do you see the ringing at the bottom of that green signal? That tells us how fast current flow is building up. We'll see a similar type thing if we amplify the red trace and look at it real carefully. We'll see ringing there as well. What I've got here is a complete picture. I've got the current that builds a magnetic field around the coil. I've got the thousands of volts that are generated as a result. Over here is the spark that's going to result when I turn current flow off. I like to see this spark last a minimum of 0.9 milliseconds. We're going to measure that because if I've got a weak coil, my spark will be too short. Now remember, we're testing in a service bay. We're not putting this under the most severe conditions. We like to see 1.5 milliseconds of spark because that's 50% of the time it takes for the flame front. So look how all these tie together. The spark is produced by the blue signal turning off, the amplifier cutting off current, the magnetic field collapsing, generating a high voltage which causes a spark. What would be different with a 2-wire? With a 2-wire, We don't use the blue control signal. Remember, in the Ford example, the PCM turns current flow off and on. That's the big difference. It doesn't have a control signal. The PCM acts as the module. In a 4-wire, there is a module inside the coil unit. PCM supplies ground to start current flow in this, and we'll get a secondary pattern that looks like this, or a primary pattern. And we'll talk about those two things. Here is our current flow. We want to look at it just by itself, because it builds up slowly at first. If it goes straight up at the front end, like it does at the back end here, we have a shorted coil. If the coil is too high or too low. So what you're going to need is you're going to need a specification. It should match specifications. Now here's one we pulled out of our spec CD. They should be between 6.7 and 7.3 amps. And they typically last 1.3 to 1.6 milliseconds of rise time. That's how long it takes it to rise up. And we'll have a number of different patterns there. But the point we're going to make is we're going to look to see if it reaches the right point, if it starts slowly and builds up, and if it drops clearly. That tells us what's going on. Peak amps will be low if B plus or ground have a problem. Doesn't matter if it's a 2-wire or 4-wire cop unit. Back to basics. Do you have good B plus? Do you have good ground? Remember, ground comes from the PCM in a 2-wire system. So the PCM have to have a good ground in order to supply a good ground back to this. And we're going to show you some other ways to test that. But here, start back at the basics. Do you have good B plus? If that signal doesn't reach its full, start with the basics, check B plus, check ground. How do you do that? Well, we're going to come in and we're going to take our test leads, we're going to hook into the COPS unit and use our diagram to locate what we'll be testing. This is normal ground voltage. Now let's look at this. It's going up. What's happening? This is the buildup of current flow in the coil, raising ground voltage. We use voltage drop testing. Anytime we pass current through a device, it's going to drop a voltage if it does work. Now let's look and see how little we drop. Our peak amperage here is between 15, let's make it like this, between 150 and 200 millivolts. Between 0.15 volts and 0.2 volts peak. Why do we use this? Well, if we look at ground on here with a DC voltmeter, we're going to read the average, and the average here is about 100 millivolts. 0.1 volts. Look, part of the time it's below 0.1 volts. Part of the time it's above 0.1 volts. If you've got a bad ground, these peaks will be much taller, and they'll show up much bigger on the scope. It may only look like maybe it's only up 150 millivolts on a DC voltmeter. But look what 150 millivolts would mean to the peaks. They'd be way up 300 millivolts, 400 millivolts. Bad grounds will show up very clearly here. So using this voltage, we can check the grounds and we can check B plus. Yeah, it's 14 volts. Good deal. We want to see it within about a half a volt of battery voltage. And remember, the battery must be charging in order for this to work properly. We have to have good ground and good power. And does it get to the module? Here is a module we found a few years ago. Had a low coil current. And the people said, well, we checked power, we checked ground. We can't figure what's wrong. We looked at the connector. Is there any reason you have any doubt? Now, this, if you cannot tell from the red mud, was a flood car. People keep saying, well, what's wrong with flood cars? You put new upholstery in. What's wrong is lots of connectors look like this. We had water in here, even though it's a sealed, it was a high mileage flood car problem. One of the things we see is weak connector contacts caused by thermal stress, where the connectors become weak and no longer function tightly. Now we've got a couple other bad things to show you here. Ford says, do a wiggle test and visual inspection of the wiring. That's miles of wiring in this car. Remember, we got to a specific function because we found something that didn't work. And no, these are not off of a coil on plug unit. But they go to show you when you have a specific circuit to go look at. Look specifically at that circuit and do pay attention. And you can see the corrosion. And do the wiggle test. We're not saying go check all the connectors and move all the connectors. We used current flow in the signals to get us to a specific coil unit. And we moved it and we found it changed. Could be a DIS module, could be a distributor, or it could be a coil on plug. Doesn't matter. Principle's the same. Look at the basic stuff. Don't let it trip you up. How can we tell we got full voltage? Well, let's start analyzing this pattern real quickly. We're going to look at a primary pattern from a Ford. First, we're going to check for B+. Now, the arrow has moved over here to the left. It says it's better part of the way to 20 volts. So it looks like to me we've got our 14 volts we're looking for. Now, see what we're doing? We're checking some very specific things. We check for battery voltage right here. The next part of the pattern is low. And by George, look, it's down near 0. And it's nice and flat. That's when we have current flow. This is a voltage pattern. When we supply ground, voltage goes low if the ground is good. And then at the end of this time period, we're going to release the ground and it's going to cause a spark. Now it goes well, real high here. But I'm going to tell you something we did. Look at our voltage scale. We're on 200 volts, but we've got the red exclamation mark saying you're off scale. Well, I can tell you this voltage is really 380 volts. But in order to get a good look at spark, we set this up for 200. If we're measuring this peak, we'd be on the 400 volt scale. But let's look at that spark and talk about our spark. It's nice and flat. It lasts about a millisecond. This is a normal pattern. When it gets through, it does some ringing at the end. What we've done here is we put secondary and primary together. We have two different voltage scales, so let's keep them right. The red scale on the right is thousands of volts. It goes from minus 4.5 kilovolts up to 9 kilovolts. That's the red trace. The red trace measures on kV, starts here and goes up. The blue trace is our 200 volt scale we're just looking at, and it goes over to the right. But look, other than the voltage scales being different, one is an image of the other. I get a little more oscillations at the beginning of the spark in the blue trace than I have in the red trace. That's because I'm looking at a finer detail. What happens in the secondary shows up in the primary. That's the point we're trying to make. Look at this problem. We have the same control signal. We have the same primary current we had before. But in our secondary, we have a little short spike. Real short. Like less than a kV. And there's no spark. Here's what we know. Coil resistance and coil current and the control signal are all normal. This is obvious. The COP unit itself is bad. It has no spark. But we know we got proper voltage. We know we got a good ground because we have normal primary current. Now this is what we're trying to say. Utilizing this type of diagnostics, you have definitive answers. Now we could look at all of the coil units and look at the kV, look at the spark time, and do a secondary analysis or primary analysis because we showed you they're very similar. This is a bad secondary pattern. It only went bad once in a while, and it's a bad breakdown not in the coil but in secondary insulation. It comes and goes, and we had to put an arrow here to say, hey, watch this spot because there's not always a spark. We can see it in primary, we can see it in secondary. We have an entire section on analyzing secondary and primary. Go there for more details because we're going to talk about looking at fuel lean out and other things. And the reason we mention fuel lean out here is one of the things we believe, or I should say I believe, I have made an observation that frequently when I have high failures rates on COP units, I have lean fuel mixture because of dirty injectors. How do you make all of this a part of your diagnostic routine for your shop? We don't recommend you stop and do this on every car. No, just the opposite. We recommend that you do your current diagnostics to locate the easy to locate problems. We call them Easter eggs. Easter egg it. If there's something that's obvious, change it, fix it, and get it out the door and make the money. Use this for the big guns. We call them profit robbers. We want to stop those cars that cause you repeated problems. For instance, how would you utilize this in the discussion we were just talking about? Looking at lean fuel mixture. If you had frequent COP failures on a customer's car, maybe it's time to go deeper into diagnostics and find the root cause of the problems that's exacerbating the problems. Yes, Coil On Plug units, Coil On Plug units, they do have a failure rate, depending on the manufacturer. We have people tell us, oh, every time I see one of these on XYZ, it's the COP unit. And we come back and we say, yeah, but look, you had a lean mixture. You didn't find the root problem. So when you get into something that's harder than normal, that's when you pull out your scope and your big guns. Don't waste time on routine problems. You should use it some at the beginning to learn to utilize it and become familiar. Once you get good, only use it when you need the big guns. After your first attempts doesn't work, do a more detailed analysis with your lab scopes. Now you've seen the type of results to look for when you're testing Coil On Plug units and Coil On plugs. So you know how to look for that. Use the other training sections to study low amp testing, to learn more about secondary and primary waveforms, to do more analysis on things like analyzing the crank and cam. Because remember, this is all controlled by the crank and cam sensor. So this is going to help you diagnose your Coil On Plug and Coil On plug systems.